put it on this computer. Minimize this. Okay, so last week I gave you a few problems to do from the beginning. Okay. So basically, last week I gave you, so this is what I gave you. In other words, I gave you a beam that had an overhang here. Let me just, I like to annotate sometimes. So I had a beam that I gave you an overhang here. The support was here. The support was here. Okay. And I'm going to repeat this one more time because it's very important, guys. You should try this on your own. Okay. Do an analysis with one type of support, do an analysis with a different type of support. You'll have totally different results when it comes to your analysis. I just want you to keep that in mind. Okay. Now, I know you don't see it here, but basically, these are still red back here. But like I said, this is because these are the reactions if you're ever doing a three-dimensional analysis. So you don't worry about these ones. But remember, if you see a red dot here, if you see a red dot here, that means you have not released the beam, and therefore the beam is considered to be fixed at the support, and therefore it's going to not allow the rotation of the beam, and therefore you're going to be getting a moment developing in the member here. And that's, you know, if that's the case, that's the way it should be modeled. If not, so a red dot here and a red dot here means you haven't released it. In other words, you haven't released the MZ because the rotation is about the Z axis, okay, and so on. And of course, if you see a yellow line here, if you see this is red and this is red, like if you see yellow here, that means you are restricting it from up and down, therefore, and you're not restricting it from side to side, therefore this is considered to be a roller. In other words, you're allowing displacement in the X direction. And this means that you have released it if it's not red, and that you're not allowing the displacement neither in the Y nor the X, and therefore that's a pin. A pin means that you're not allowing displacements in the vertical and the horizontal translation, but you're allowing the rotation of the beam. Just repeating that so that you guys can make sure that you're on the right track. Because guys, with computer programs, the way you model it, the input you put, the computer program doesn't read your mind. Garbage in, garbage out. That used to be our old adage when they used to come computer programs, because they'll just do it. They're very obedient slaves. They'll just do everything you tell them to do, but they're based on what you're going to be telling them to do. So this was a problem, okay? And this was the length of the members. And of course, these were the loads. We had a concentrated load here. We had a distributed load there. And I should have put the reactions. I forgot to put the reactions, but this was a shear diagram. Okay, this was a shear diagram. Now, if you see the shear diagram in the other directions, because I haven't flipped it, okay? So in reality, this should have been like down, that should have been up, and so on. I should have had the mirror image. I didn't flip this shear diagram. So this is the shear diagram, and it makes sense. And of course, if I want to know the reactions, simply add these two together. That will give me the reactions. And of course, the moment diagram. Now, I don't know if you guys remember, I don't know if I gave you this as one problem to do manually, so that you can see that the results by ADA are very close or exactly the same way as if you did it manually. So here you have this one. I did flip properly because the negatives are on top and the positives at the bottom. So that was the shear values, and that's the moment values. So if you guys have got the right values, you're doing great. If you haven't, well, there could be something that you need to go and tweak in order to get these values. So that was problem number one. Now, problem number two, very similar. The only difference was we had, okay, I think there was a moment here, and that we had a concentrated load there, and we had a distributed load across the whole thing. I don't, because like I said, unfortunately, ADA doesn't show the moments here, which I find a little bit of a nuisance, okay? So there was a shear diagram, okay? And of course, the moment diagram, and there's the moment. And if I'm not mistaken, okay, the moment was in this direction, therefore the tension is at the bottom, and therefore it's considered to be a positive moment because the tension is at the bottom. That's the way it's twisting the material. So here, in other words, it's twisting like this. All the fibers here are being stretched, and therefore that's what causes tension. And at the top, all the fibers are being compressed, and therefore that causes compression, okay? And that's the only thing you have to remember about moment diagrams. Tension, compression. Positive, it's the tension side of the beam. Negative is the compression side of the beam. That's all it is. So none of this counterclockwise is positive, no, nothing like that. That's just sign convention to write your equation of equilibrium. It's got nothing to do with where's the tension side and where's the decompression side of the beam, okay? And clear all drawings. Now here, I think there was another moment here because I see a drop here, okay? And if you look, I think the I don't remember if the moment was clockwise or counterclockwise, okay? But if you look on this side of the beam, okay, so therefore, if you look at this, you can even realize why it goes down, because this means that it is causing compression on the top of the beam, and therefore it went down, and then it went back up, and then it went back down. So that's how, okay. Anyway, and what's good about ADA is that if you run ADA and you get your results, and if you do one manually, it helps you to understand how you can do them manually. So, you know, like, and if it will correct you if you want to practice on how to do these moment diagrams correctly. It's up to you. I mean, no.
Sir?
Yes.
Isn't question 2 in imperial units instead of metric?
Did I put it in metric?
Yeah, I mean, question 2, I think it's in imperial.
Is it? I'm not sure, Jimmy. Maybe the members are in imperial, but the forces are in metric. Is that what it is?
Okay.
You know what I mean?
Yes.
So and be careful, okay? Be careful, guys. Like when you're looking at your results, look at your units. I mean, I had a third-year student. You know, we were doing a project with ADA. I had a third-year student saying, "I did everything I did everything that you said, but my results aren't like yours." Okay, and the problem is that of course he had modeled everything in imperial, and he also asked for the results to be imperial, and he was looking at the results in imperial, and the results in imperial were slightly different than the metric ones. And when I looked at his, when he sent me the email, I told him, I says, always look at the values here. In ADA, it will always tell you what the values that you're looking at in this table. So make sure that it's in kilonewton meters. If it's in kip foot, ADA will tell you what are the, and that's why it's very important that somewhere on your diagram, somebody knows what, in other words, is this 23 kip foot or is this 23 kilonewton meter? So it's very important. The units to me, guys, are the most important things in these problems, okay? Because you have the wrong units, I don't care what the value might be right. If the units are wrong, then it's wrong as far as I'm concerned. But if I'm not mistaken, Jimmy, I'm sure that
the loads are in imperial also.
they are. So I'm giving you the values in metric. Is that it? Or did you guys have the same values here?
Yeah.
So maybe something.
Well, I have a different moment diagram.
You have a different moment diagram.
Mine's in imperial. So.
Yeah, so therefore I probably made a mistake. I should have put this in imperial. I apologize. I can go back and open up the thing, but okay. This one here, I don't, okay. So is this for number 3? Is this okay? I should have double checked. Is everybody got this for number 3?
Yeah, I have the same diagram.
Okay, and you have the same moment diagram? Oh, I know what I did. I copied the wrong moment diagram from the slides, guys. This is, so what I showed you before was probably the moment diagram for problem number 3. I apologize. I'll show you the right one. I got it stored somewhere. What I did is I went and pasted the wrong diagram for problem. Like if you look here, if you look here, I put the same problem number 3 and problem number 2. I put the same moment diagram here. So I made a mistake. I went to cut and paste the wrong diagram. So that's what it is. You understand? So I apologize about that. I should have realized that because I did this very quickly. So Jimmy, you're right. This is the same moment diagram as I'm showing you problem number 2. And number 3, this was the load. There was a model, and that was a shear diagram. Is everybody okay with problem number 4? Can somebody give me a heads up if it's okay?
Yeah, this is good.
Okay, thank you. So like, I apologize. And therefore, this should be the moment diagram for problem number 4. And that makes sense to me. Yeah. So, and last but not least, okay, problem number 5, like I said, problem number 5 is going to be the type of problem you're going to be getting on the test. So in other words, you have to learn how to release, how to create a smooth pin, okay? And we're going to be doing a lot of smooth pins today. I mean, pin connections today, because we're going to be doing trusses, okay? So what you do is that you pick the member, okay? You pick the member, and then in the properties, you're going to have here MX somewhere, and then you fly out the menu and you have different options, okay? Plus means that it's fixed, it's a continuous member, and then you're going to have a plus with a 0, or you can have a 0 with a plus, depends on which, remember, which is your I and which is your J, okay? And then you can have a 0, 0, and that's if you want to release it on both ends, okay? So that's how you release it, and if you don't release it, then your analysis is going to be slightly off, okay? That's number 1. And number 2, so that these were the loads, and everybody should be able, you know, how to put a triangular load. In other words, when you put your distributed load, put one side 0, put the other side the value that you have, you'll get your triangular load with ADA. And here, this was the shear diagram, and you'll notice that ADA is pretty accurate, because since here I have a triangular load on the shear diagram, it's parabolic, and that's what it should be, okay? Now, unfortunately, I did not copy the thing like to scale the shear in a moment diagram, but I just want to show you something, okay? In the moment diagram, what you need to realize is that a pin means that it does not resist the rotation of a beam. So where the pin is here, okay, where the pin is here, the moment should be equal to 0. M is equal to 0, and that's exactly what we have. So our pin is right there, okay? And I think you guys did this one manually on one of the assignments, and I gave you the same one again, and I think most of you got this on the assignment. And I gave you this one again and again. So where the pin is here, right here, okay, remember the moment is 0. So if all of a sudden you're looking at your moment diagram and you don't, and you look at it and you look at the where the pin's supposed to be and the moment is not 0, that means you haven't released it, and that tells you right away that you haven't modeled it properly. And like I said, it's pretty good, because here it should be quadratic. Here it should be quadratic. Here, okay, it's quadratic. And then here I think there was no more load, and therefore it should be linear. And then of course this is not even quadratic, this is cubic. Okay, so this is a cubic curve, which looks very much like a quadratic curve. And that's it. And if I apologize for putting the wrong solution for problem number 2. I'm sure that if I go look for it, I'll probably find it. So does anybody have any questions on the beams? Because if you want, I can review something, or is it pretty much clear on how to model a beam? Does everybody feel comfortable with it? Now, what I can do, hold on a second. I apologize for that. Now, let me just go back to my, go to the, yeah, okay, so I stop sharing. Share, and so guys, this is the solution to problem number 2. Do we agree?
Yeah, I got the same.
Like I said, I apologize. I went to cut and paste it in the wrong place on my thing, you understand? So this is the solution to problem number 2. Okay, so like I said, I took the moment diagram of problem number 3 and I pasted in problem number 2, and I should have just cut and paste this one into the PowerPoint. So I apologize for that, but there's a solution for problem number 2. Okay, so if there's no questions today, what we're going to be doing is we're going to be learning how to model trusses, okay, on the whatchamacallit, on ADA. And so we're going to go ahead and okay, stop sharing. Okay, so let me just put up the okay. So guys, just to make sure that we're on the same page, do you guys see a split screen on your screen? In other words, you see the PowerPoint, well, on the left-hand side of your screen, and then the ADA on the right-hand side? I just want to make
Yeah.
sure. Okay, great. Because I find that this is going to be the easiest way for me to sort of like look at the diagram and be able to do it on ADA at the same time. Is that okay with everybody? Okay. And at the same time, okay. Thank you, Emmanuel. Now, guys, we'll talk about trusses. And here I'm just giving you some, I'm just giving you some trusses that have names, okay? And why do you think trusses have names, guys? Does anybody have an idea why should we have names to trusses? Does anybody have any idea why this truss is called a Pratt truss? Why is this called a Howell truss? Why is this called a Fink truss? Why is this called a Parker truss? Why is this, you understand? Like, in other words, why do these trusses have names?
Is it named someone after who invented?
Exactly, guys. Back in the 1900s, okay, when bridge building became very, very, like, for example, when they were, like when they were extending the railroads across, especially the United States, okay, when they were extending the railroads across the United States, bridge building became a very, very, busy, very, very, busy thing to do. And these, well, engineers, okay, or Pratt, Howell, and all that, okay, what they did is that they showed people on how to use their truss and how to analyze and how they get the results of their analysis, and they would have patents. So if if a railroad company would want to design and build a Pratt truss, and they would want to use Pratt's truss for their bridges, they would have to give Pratt a royalty. Okay, so these guys had patents on these designs. Okay, and that's how and that's why these trusses have names. And some of these trusses, like for example, these look very similar, right? Like in other words, this looks like the Howell truss looks very much like the Pratt truss. Okay, the only difference is that the Howell truss, the diagonal members go up here, okay, as opposed to down. Well, what happens is that depending on the direction of the diagonal members, of the web members, okay, they can either be in compression or in tension. And of course, steel loves to be in tension and not in compression. So if you can take the shorter member and put in compression, it's much more beneficial than taking the longer member and putting in compression. Okay. Now, so these are the trusses. Okay. Now, I want you to look at this truss here. Okay. And they call it a K-truss, right? A K-truss, basically what it does is that it takes the vertical members and it forms a K with it, and it laterally supports that member. Okay. Now, the next time you guys happen to be downtown and you happen to look at the Jacques-Cartier Bridge, even though the Jacques-Cartier Bridge has this, this type of a shape. Okay, next time you look at the Jacques-Cartier Bridge, believe it or not, the Jacques-Cartier Bridge is made with K trusses. Okay, so next time you look at the Jacques-Cartier Bridge and take a look at it, you'll see the Ks and the whole, even though it's got this parabolic shape, don't worry about that. It's not the shape of the top chord, okay? It's basically the shape of or the geometry of the or the triangulation and the direction of the web members that determine what kind of a truss it is. Next time you look at the Jacques-Cartier Bridge, you'll see that it is a K truss, okay? Now these are very, very popular. Like if ever you look at old railroad, bridges, okay, they were all, most of them were done with this Warren Truss here and so on, okay. So like I said, this is just for you to have some general information so that when people say, hey, well, what about a Howell Truss? Well, this is what you have. And what about a Pratt Truss? What about a Warren Truss? So these are the three more popular ones that used to be used way back when. And then the K-truss is, like I said, you know, we have a very, very famous structure that's made with the K-truss, and that's the Jacques Cartier Bridge, and so on and so on. Okay, so that was just to give you some general, you know, information so that now, when it comes to trusses, guys, this is something you should learn, okay? Because if you're going to stay in the field, and even if you're not going to be, I don't care, like you don't have to become a structural engineer, because, you know, like this is just so, like if you happen to be speaking with a structural engineer, if you're a project manager, or if whatever you're doing, and you're speaking with a structural engineer, you should be familiar with the terms of a truss, okay? Because this way, if the guy's, he's telling you, the top chord, the bottom chord, the web members, the panel points, the panel, you should be able to visualize in your head what this means, okay? So this is something that I would strong, like guys, number two, okay? The more you learn about the glossary in the industry, the easier you're gonna make your life. I can tell you right now, okay? I mean, it's easy for me because I've been doing it for over 40 years, and therefore I have a lot of glossary in my head. But I can tell you right now, the glossary that you guys learned in, for example, construction 1, construction 2, the more you can retain that glossary, the easier you're going to have a time to understand people when they're talking to you, the easier you're going to be able to express yourself, the easier you're going to be able to write your report. So I do strongly recommend that try to retain as much of the glossary as possible. And of course, using the right terms, you can be very, very specific at what you're referring to, and therefore you're only doing yourself a big favor by, you know, learning this stuff. So now, when it comes to trusses, okay, this here is called the top chord, okay. Now in this case, okay, so this is the top chord, and this here is the bottom chord, okay. So basically, okay, so this is the bottom chord. So, and then of course, these are the web members right here. Okay, now some people like to say web members, and for example, if you happen to have a vertical and diagonal, some people like to refer to this as a vertical web member, and the diagonal web members, the ones in between are web members, okay? And what these web members do, they actually transfer the shear that are developing, because this is basically, guys, all a beam, a truss is a very, very well engineered beam, okay? It's like having a top flange, a bottom flange, and a web member here to transfer the shear. And that's what a truss actually is. It's just a very well engineered beam, okay? So this would be like top flange, the bottom flange, and the web of your beam. So now these are the web members. Now panel points, okay, are where the members meet. Okay, so these are panel points. And these are panels. In other words, this is the panels, okay? So in other words, this is a panel, this is a panel, this is a panel, and that's a panel, okay? So those are the, okay, and then, and of course, this, I gave you a little detail here that goes into more detail, but that's up to you if you want to go into them. But, and then you have here truss plates and so on and so on. But what you have to really worry about is the basically the top chord, bottom chord, and web members. You should at least realize what those are. Okay, so somebody's telling about the bottom chord, he's talking about the member that's at the extreme bottom of the truss. When he's talking about the top chord, it's a member that's at the extreme top of the truss. It doesn't matter what shape it is. And the web members are the ones that go in between the top, extreme, and the bottom. So that's what you have to remember. This is just some terminology for you to be able to, you know, understand the different you know, the different names that the truss has, okay? I mean, I don't even want to get into this. As a matter of fact, we will be modeling one of these as a last example, okay, which is a very interesting one to do. Now, what I'm going to do is, of course, the best way to show you how to model a truss on ADA, and this, we're going to take our time, okay? We are going to now model this truss. So what we have here, okay, we have, for example, a support here, a support here. This truss has a span of 54 meters, and I don't know if you guys appreciate, but 54 meters starts to be a nice span, okay? And here, when you're loading a truss, you normally load it at the at the panel points, okay? This is where the loads are applied for a truss, okay? And of course, what you can do, okay, what you can do is like, Normally, as a matter of fact, the way a truss is actually analyzed for a bridge, okay, you have a moving load that would go across here, and it would be to analyze this member here. And then after that, you would see what the forces are at the panel point, and then you would analyze the whole truss based on what the maximum force that created by that moving load. But that would be, you know, like, that's not what we're doing here. We're just going to learn how to how to analyze the stress with ADA. Okay, now in this case here, okay, when I talk about the top chord, okay, so this here is not a web member. This is part of the top chord right here. So this here is the top chord. This here is the bottom chord. Okay. And of course, everything in between are web members. Okay, so this, even though this is at a diagonal, this is part of the top chord. Okay, just keep that in mind. Now, here I'm giving you the material. Okay, the WT, okay, is the type of steel that is normally used for bridge, because this is what we call welded top-notch steel. In other words, it acts very well under at minus 40 degrees. That's the only reason why I gave it to you here. But like I said, it doesn't make much of a difference for ADA. If you're using steel, whether it's 350 WT, 350W, I'm pretty sure you're going to get the same analysis. The only time that makes a difference is when you want to do the stresses with ADA, then it will take this into consideration, okay? Because ADA takes the E to do its analysis, and therefore it's the same E for all the structural steels, I believe. Now, so here what we're going to do now is analyze this thing. And what's nice about ADA, okay, now I'm going to come here. Okay, so let's start a new file. Let's start a new file. Okay, and of course I'm going to, now when you start a new file, I strongly recommend you go under file here. Okay, I strongly recommend you go under file and you go to project configuration, just like you've been doing so far. Okay, and under project configuration, okay, here you can, of course, give the details of what you're doing. So this way, if ever you're printing out something from ADA, it will be on the cover page. You'll be able to use that as your cover page. Now, as far as the preferences goes, okay, now, as soon as I open up a file, by default, AD has metric shapes and metric units. So, and our problem here, we have metric shapes and metric units. And how can I know that I have metric shapes? Well, when you start seeing 610, well, the biggest imperial shape that you have, okay, is 44 inches. So therefore, you know that, and then, so you just by seeing the first number here, I know I'm in metric, okay? And of course, my geometry is in metric. So like I said, I think we did this last week. You can have imperial geometry and metric shapes, or you can have metric shapes and imperial geometry. So you can pick and choose here. And if it's metric, of course, make sure that these are both on. And like I said, if you see the blue around this one, that's what you're working on. And these dialog boxes, of course, okay, are something you should remove by default. They're always checked on. So this way they won't pop up in your face every time you add a member or do something. So, and as far as the analysis go, if you ever want to get, 20 results per member, 100 results, this is where you change them. I don't bother with that. As a matter of fact, for trusses, I'd like to bring this down to 2 results, but I'm going to leave it at 10 for now. It doesn't make a difference. So everything's good here. Okay. Now, what I like to do, even before I start modeling or anything, okay, what I like to do is I like to go to ADA and ask for my member lengths, okay, and of course my shapes that I've assigned. If I want to put the material, you can also put the material, okay, but I want to see at least that on the screen as I'm putting in the information, so I know if I'm making a mistake or not. And then at the end, I can come back and double check, okay. Now, sometimes if I want to make attributes, and I'm going to do it for here, okay, I'm going to click here end conditions to see the end conditions, because we're going to be, and I'll explain to you why we're doing this later on, okay. And of course, graphically, I don't like to see this big X and Y axes on my screen. I find that it takes away from, so therefore I like to remove that. This is my own personal choice. You can leave it as if you wish. You press apply. Okay, and now you've cleared up that screen. Now, of course, you don't see anything because you haven't done anything yet, okay? But this is how I like to start all my AD. I go through my preferences. I make sure I'm in the right units. I make sure I remove those dialog boxes, number one. leave it in 1 and 10, good enough. And then I go into my visual graphics and I start making sure that as I'm modeling, I can start seeing things visually on the screen. Now, I want you guys to go up to the ribbon here and see, pick where it says Truss. Can everybody find that icon? So at the top of your screen, if you have ADA on, you should be able to find one that says Truss. Are we all good? Can I click on it now?
Yep.
Has everybody clicked on it? I want everybody to click on it. If you click on it, this is the dialog box that pops up. Okay. Now, excuse me. Like here you have two categories. One is a bridge truss and the other one's a roof truss. Now this is pretty well a bridge truss, so we're going to go through this one here. Just like if I pick this radio button here, it gives me a preview of what the geometry looks like. Okay. And if that's the one I want to use, okay, if that's the one I want to use, then I would start putting in the information here. Okay, that's number one. Now, you'll notice that this one looks very similar. Okay, it looks very similar to what we're doing. In other words, I have a diagonal member there, I have a diagonal member there, same thing here. But this diagonal member goes this way and this one goes this way. So I might not want to use a Warren truss to model this, because then I'm going to have to do more modifications. So I'm going to try to find something that is either the same geometry or as close as possible, so I can do as little editing afterwards as possible. And therefore, I'm going to go look at what my options are. So I'm going to go look at what my options are. Now, sorry, I want to do a mouse. So now, if you look at the Pratt truss looks pretty much what we have. So in other words, this is a Pratt truss, because if I look at the diagonal member here, and I look at this diagonal member, they seem to be, so this seems to be what I want, okay? Now, we're going to click the other radio button. The Howell truss is not what we have, okay? And definitely we don't have, this is a Parker truss, okay? So if you have something that's got a nice bow in it, okay? And of course, the Baltimore truss, which is, and then the K truss is something I really like, you understand? And so on, and the Petite truss, okay? So these are all the different bridge trusses that, and like I said, just because if you're, and as a matter of fact, we're going to be doing a couple where we're not going to have exactly the same geometry, but we're going to start with the one that is as close as possible to our geometry, and then we'll modify it to our geometry. So it's a good starting point. It's going to help us save a lot of time creating nodes and so on and so on. So let's go back to let's go back to the Pratt truss here, okay? And then we'll do the roof truss on the next example. So now, here, once you pick this is what all you need to do here is put 3 pieces of information. Okay, one is a span. So the span goes from support to support, and in this case here, it's 54 meters. So put 54, okay? And all it needs to know is the height. The height here, of course, is 6 meters. And then the number of panels. So 1, 2, 3, 4, 5. I have 6 panels in this truss. So I'm going to put 6. And that's all you need to do. And ADA will do the rest, okay? Now, this point of origin here, ADA wants to know where you want it to actually place this truss. So leave it at 0, 0, 0 if you don't have anything. What's nice about this program is that, for example, if I happen to, let me give you an example. If I happen to, okay, if I happen to have a structure here, okay? I have a structure here modeled in ADA, for example, and all of a sudden I have another structure here modeled in ADA, okay? And I know that I'm going to be putting a footbridge across here, and the truss is going to go right in here, okay? If I know where this panel point is, I know where this node is, I can actually give it the coordinates here, and then ADA will stick it right there for me. So that's why. If ever you need to add a truss, it's somewhere particular in your modeling and you want ADA to put it there for you, you can actually put it there. So if I knew that this would be supported right here on this thing, I can actually give it the coordinates and ADA will stick it there. But since we don't have that, we'll leave it at 0, 0, 0. Okay, so we're going to leave it at 0, 0, 0. Now, if you're happy with all the input here, and don't forget, if you make a mistake, you just delete the file, start one over, so don't worry about it. It's not the end of the world, okay? That's number one. So I press OK, and look what happens. Okay. Now I'm gonna have to zoom out a bit because I'm only using half the screen. But basically, there's your truss. Isn't that nice? That ADA did that for you. Okay, so it has now. I know like you won't see it, but it has the member lengths are there, which is right. 9 meters. 1, 2, 3, 4, 5, 6 times 9 is 54. This is 6 meters. So I know so far so good. It's pretty much represents. So did everybody get this? Did you check to see if you had the right member length and the right member height? In other words, did you check this member here to make sure it was 6 meters? You check that to be 9 meters. Don't worry about that. That, of course, if you use Pythagoras theorem, it should be 10.82 and so on. But is everybody okay with this? And guys, I can go back. Who doesn't have this on their screen right now? So are we good to go, to continue? Or is somebody not there? Please let me know now, because I can go back. I can't see anything and I can't hear anything. Pardon?
I think we're good.
Thank you, Emmanuel. Appreciate it. Like guys, keep in mind, I'm here. I'm trying to make sure that I don't lose you. And at the same time, like I don't have anything visual to be able to see if you're there or not. So, okay. So now, these, you'll see these are all members. Okay. They haven't been assigned their properties yet. Now, what I want you to do is make sure you're on active node here. Okay. Active node there, number one. And by default, it should be there. Okay. I want you to pick this node here, hold the control button and go to the other end and pick that node there. And I want you to right click and I want you to go to properties. And of course, I want you to change this to a support node. Now that's become a support node. Now I've changed it to a support, but by default, ADA is fix, 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 fix. In other words, it's a fixed support. That's not what I have. What I have here is I have a pin and I have a roller. And bridges, believe it or not, they have pins and rollers. And these rollers are basically the expansion joints that you feel when you go over the bridge. That's where the roller is. So now, change from activate nodes to activate supports on the vertical bar. Okay, so you went from activate nodes to activate supports. I hope you did that. Because now what you're going to do is you're going to go and pick this one. And of course, you're going to change it into this one's a pin on this side. So therefore, that means it cannot move in the X. It cannot move in the Y. But it is free to rotate about the Z axis. So therefore, I'm going to go free MZ. Okay, so this is, you're not allowing any displacement in the X direction, no displacement in the Y direction, but you're allowing it to rotate about that support. And therefore, you press OK. Now, of course, you don't see it, but that little red button that we had there is gone. Now, I do the same thing on this side here. The only difference here is that to create a roller, I have to let it go free to move along the X direction. It's fixed. I don't allow it to displace around, and therefore, I let it rotate about the Z. So freed in the X direction, free to rotate, but not free to move up and down. And therefore, that's a roller. And if you zoom in, you'll see your little red dot is gone and you should only have one yellow line going up and down.
Excuse me, sir.
Yes.
It doesn't let me select them.
I'm sorry, because first of all, yeah, which one are you at? Are you here on the activate node? On the
activate supports.
Okay, but first, did you change it into a support? In other words, first you have to go to nodes, pick the node.
Okay.
Okay, I'll pick another one, but I won't do it. Like for example, I pick both of them at the same time. I pick that one, hold down the control button, and I pick the one at this end. Do that, number one. Did you do that?
Okay, yeah.
Okay. Now, once you pick that, okay, so for example, I'm going to do it for this node here, but I'm not going to change it, okay? Okay, I'm going to go to properties. I'm sorry, let me go. And okay, see here where it says change it to support node. You have to change
Oh,
the node.
okay.
Yeah, if you don't change it to support, the program doesn't know that you want to convert that node into a support. So you have to put into support node.
Okay, yeah, I see.
Okay, so now I'm going to cancel that. Now that you change the ones at the extreme here, okay, once you've changed that to support nodes, now you can go down and pick supports here, activate supports, and now you go pick one and make sure you modify it into a pin and the other one into a roller.
Okay, yeah. Thank you.
Does that make sense? And the way you could have seen it on the screen is that if you didn't see that, see, because supports have red, 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 you understand? If you didn't see that on the screen, that means you hadn't changed this into a support node. That's how you can graphically see if you did it properly. So here, for example, it's yellow, no longer red, and these two used to be red, now they're yellow, so therefore that's a pin. And if I go to the other end, I'm gonna have only one yellow line and a red dot, and that's what I should have at this end. And that's exactly what I have. I have a yellow dot, means I released it, and I only have the restrictions in the Y direction, therefore that's considered to be a pin, okay? So I'm glad you asked, guys. Like, if anything is not happening, please, it's because you're not, you know, it's like anything. There are sequential steps that have to be done in order for the program to be able to execute the command you want it to execute. And don't be afraid to tell me it's not doing it, because I'll go back and I'll show you where you might have overlooked one of the steps. Okay.
The configuration that you did on them.
I'm sorry. Can you repeat that?
Yeah, can you go back to the node characteristics for the supports that you did?
Okay, so why don't I, okay, so what, like, it's too bad. Okay, I'm gonna undo. Okay, so right now I've undid everything I've done so far. Fair enough? Okay, so Emmanuel, is this what you see right now? In other words, if you zoom in, you're gonna see a regular node here.
Yeah.
Is that what you have, right?
Actually, mine are
Pardon?
mine are supports, but they're not like configured correctly, I guess.
Okay, so let me go back. Don't worry about it. Okay, so now number one. Okay, so number one. See, right now, look where I am on my vertical. I'm at activate supports. I won't be able to pick anything because I don't have any supports. So I'm gonna have to go to my nodes first. Okay, so this is very important. This tells the program, well, what do you want to work with? I want to work with the nodes, I want to work with the supports, I want to work with the members, and then of course you can, this program, you can, model plates, and I don't want to get into that. You can model, floors, and you can model walls, and so on and so on. Okay, so right now, so what I'm going to do is, of course, I'm going to activate the node, and I'm going to go pick this one, and since I want to change both of them, I'm going to hold the control button and do the other side. Okay, I'm going to see, since I picked two, I'm going to go to properties, and I'm going to change this to a support node. Make sure that it's a support. Okay, and now if I zoom in again, like I said, okay, it is yellow, yellow, restricted, restricted, and it's red. Okay, so that means that right now it can't move this way, can't move this way, and I cannot move it rotating. So now what I'm going to do is I'm going to activate the support, and I'm going to go and change. So I want to keep that fixed. I still want that yellow. I still want that yellow, but I want to free it with respect to the rotation, and therefore I put free here, press OK, and now it's become yellow. That means this is pinned. And then if I do the other side, okay, I'm going to do exactly the same thing. Now here what's going to happen is that you see the red dot fixed. In other words, there's no rotation. That means anything that, as soon as this thing wants to bend or rotate around that point, it won't allow it. You're going to get a moment in here, you're going to get a moment in there, and that's not what you want. Definitely not what you want. So therefore, now I'm going to, double click on it. And of course, now I want to free it in the X because I want it to be able to move back and forth as an expansion joint. I want to restrict it in the Y, otherwise the bridge is I'm gonna get an error. Okay, and then I'm gonna free it in the Z, like I said, free it in the Z. Okay, and now look, perfect. I have only restricting it this way, and I'm not restricting it that way. So that's perfect. So is that okay, Manuel? Did you get it?
Yeah, I did. Thank you.
Okay, so now, like I said, once you do this, and all supports for every structure we're going to have is going to be the same 3 basic steps. Okay, so this is why it's good that you get very familiar with it. So now I've got my members. Like, guys, if you notice, I have a very methodical way of doing my model, so I don't skip a step. Okay, I like to create my geometry. After, in this case, it gets automatically generated by the program, which is really nice. And then, of course, like, even if I take something that I always make sure my geometry is okay. In other words, the dimensions are good, everything there, so on. And then after that, I go and make sure that my supports are properly modeled. In other words, I don't want to accidentally fix something when it's not fixed, or I want, you know, so I make sure my support. And then after that, I go and I assign the properties to the members. Okay. Now here, what I'd like to do is I'm going to start with the top chord. So first of all, I have to activate members if I want to pick members on the screen. So I have to make sure everybody activate your members now, please. Okay. And if it's highlighted with a bluish outline, that means that's what's been activated. Okay, number one. And if you don't activate that, you won't be able to pick nothing on your screen. So make sure you activated your members here. Now, I'm going to pick one member, and unfortunately, I cannot pick with a window here because as soon as I cross other members, it's like crossing. They should have you know, I'm going to try with a window here and see if I try with a window. See, it picks everything that crosses the window, so that's not very good. Okay, so I'm going to click that. So I'm going to pick this one here, and I'm going to hold down the control button, and I'm going to pick that one, pick that one, pick that one, hold, make sure you hold, and so now I've picked all the members that are related to the top chord. Does everybody have that all in purple on their screen? Or do you want me to go back and do it again?
All good.
All good, thank you. Now, since I picked a number of members, I right click, I go to properties, right? Just like we're doing the beams. This is a standard W shape. It's a W610 by 140. So I go to properties, I go to steel. Okay, and if you guys did the assignments, you should be able to find this. You open up the W shapes here. Okay, open up the W shape. And of course, it's a 610. So in other words, all the 610s are under this here. So I press the plus sign under the 610. I'm sorry, where's my 610? And of course, it goes from the heaviest to the lightest, and this is the 140. So I go down until I see 140, and here we are, W610 by 140. Okay, so this is a standard W shape that is rolled. It used to be rolled in Canada, now they're all being rolled in the United States, okay, in the mills. And of course, if I want to see the properties, I double click here and I get to see all the section properties and some geometric properties of that shape. That's okay. And if I'm happy with that, I'm going to press OK. Now, I'm not, since all these have the same material, I won't assign the material right now because I'll do it all at one shot at the end. Okay, so don't worry about that. So, but if I want to make sure that I include the dead load, we're not going to include the dead load in our analysis, but normally you should make sure that you activate the dead load here. Okay, this way, if you want to include the dead load of the members in your analysis, you do. I like to run my analysis once without the dead load to see if if I want to do a check, because then it becomes very complicated for me to calculate all the dead load of the structure. And then once I've checked it, I go back, I assign it with the dead loads, and I, run the analysis with the dead load. So this is okay. And of course, you don't see it here. I'm too far, but there you go. So I just want to make sure that now, as far as the lengths go, we know the lengths were okay. Okay, so all I want to make sure now is I have the right shapes. Okay, so I do have the right shapes assigned to the top chord. Perfect. Now, is everybody good with that? Did everybody assign the properties to the top chord? Are we good? Now, what I did for the top chord, of course, I'm going to repeat it for the bottom chord. So I'm going to pick one bottom member, hold the control button, and pick all the other bottom chords here. And then again, right click, go to properties, and go to, okay, and again, it's a W shape, so therefore we know where to find the W shapes in ADA. They're right here. And in this case, it's a W shape 530 by 82. So looking for 530s here. Here's my 530. And of course, I go down to 82. And I hope you guys remember that this is the kilograms per meter, the mass per unit length. And of course, it's the nominal depth of the member. Okay. And so that should be okay. Now, as far as the web members go, what's fun about this, I can actually draw a window. And since I can just cross the web members, I can pick them all together by a crossing or a window, okay? So if you want me to do that again, you just pick a point on, sorry, you pick a point on your screen and you simply cross all the members and it picks them all at the same time, okay? And here, like I said, if the diagonals were, usually the diagonal members are different from the vertical members, you know, and so on and so on. But for now, we'll make them all the same. So we picked all the web members, and of course, I will right click, properties, and again, it's another W shape, W410 by 46, go back, steel, W shapes, and a W shape, and of course now I'm going to be, it's a, we said it's a 410, so we're going to go to 410 category. And it's a 46, there's my 46, and therefore the radio button gets picked automatically there. Press OK. OK. Now, to make sure that I've got everything assigned properly, of course, I would zoom in, understand, and see if everything's good. Yeah, W610 by 140, 520, 410, 410. Everything looks good so far. Looks good, looks good, looks good, looks good, looks good. Now, here, what I like to do is, of course, if you don't assign a material, you're going to get an error message in whatchamacallit, an ADA, okay? So what you're going to do is now you're going to pick all the members by one big window. Pick them all, one big window. There should be all purple. Right click, go to properties, and this is where you're going to assign the material right away, okay? So you go to steel. Here I say it's a WG4021, so you go to G40. Steel is Canadian steel, WG40. And it's a WT means it's a weldable, tough notch tough steel. That's what that is. Okay, it's a specific type of steel. And there you go. Now, of course, to make sure that if you want to include the dead load, just put that. Now, the next thing I want, don't close this yet, okay? What I want you to realize is that ADA, when ADA analyzes everything, everything is fixed, okay? Everything is fixed. So in other words, the members are all welded together. It's all one fix. So now, when you come to trusses, well, trusses, because of the way that they're joined here, everything is pinned. So these are all pin members. In other words, this would be pinned, that would be pinned, and these are all considered to be pinned because unless, like, so therefore, what you're going to have to do is you're going to have to tell the program that I am analyzing a pin structure, okay? So what you're going to have to do is come here and you're going to have to release all the members at both ends. So you go to bending MX, you go to the very last option and you release them at both ends. So this way, what the program is going to do is going to release all the members at each panel point. And that's how trusses are analyzed, okay? Because the joints are not fixed, they're pinned together, okay? They're considered to be pinned, not fixed. So therefore, you have to release them all. And if I press OK, well, if I come back here, okay, now for some reason, okay, you'll notice that you see what ADA did, okay? Like it released this one, it released this one, it made that one continuous, but that's okay. That's what it's supposed to be. So it released all the members, okay? Perfect. And that's what you want to see. Now, to make sure that you've assigned, to make sure that you've assigned the right material, just click material, apply. And of course, all the material is there. So that to me is exactly how, okay? So ADA now has actually model this the way it's, or you've modeled this the way it's supposed to do, and ADA will analyze it correctly. So in other words, at every panel point, when you have a truss, okay, all the members are considered to be pin connected, and therefore you have to tell ADA that's pin connected. Now, here you notice that I want you to realize this, okay, and this is the right way to do it. Okay. You notice that there's no yellow here. Well, it doesn't matter. As long as 3 of the 4 members are released, this is considered to be all pinned together. So don't worry about that. There's no yellow there. Okay, that's and ADA is doing that purposely to eliminate redundancy. Okay, so that is the right way to do it. Okay, so now let me zoom out. So now I am happy with my modeling. In other words, I got the right geometry, I got the right member lengths, I got the right supports, I've got the right excuse me, properties to the members, and I've got the right end conditions of each member. So now, as far as I'm concerned, I call it, you know, step 1 of 3 steps, because I like to do into 3 particular. Step 1, I've done my modeling. Everything is good. Now, what's the next thing? Then, of course, I move over to my loads. So to move over to my loads, of course, I have to go and assign load cases in ADA. Okay, so I'm going to go to loads. I'm going to take my time, let you guys go to loads, go to load cases, and you're going to define your load case. Okay, and of course, the dead is there by default because the program reserves this to calculate the self-weight. And you just call this one live. Okay, live load. Now, if you don't want to waste time during an exam, don't assign the type. It won't make, I won't even assign the type. But if you, in real life, if you assign the type here, in other words, if you come here and you tell the program that this is a live load, and this is a snow load, and this is a dead load, if you do the automatic generation of the combination, it will do all the possible combinations that you need to do according to the building code. That's why, okay, if you don't, then you don't have to even assign the load. So this is your live load. And you press OK. Now, remember, when you want to assign loads, you have to activate the load case. So activate a load case. Okay. And of course, I'm going to be assigning my live loads. Save project. Okay. So let me go, where do I want to save this? In my case, desktop. I'm going to go to Dawson. Okay. Save. Okay, so I hope you guys saved it. Now, I'm ready to assign my loads. So first of all, everything's good here. So let me unclutter the material, the shapes, and of course the attributes. I've checked that, everything is okay. I want to unclutter this so when I go look at my results, I don't have that in my face, or on the screen, I should say. Now, here you'll notice that all the loads for this bridge have been assigned to the panel points. So what you should do is you should activate the node on the vertical column, activate nodes. Okay, that's number 1, because this way when I go pick something, I'll only pick the nodes. Number 2, you notice that they have exactly the same value. So therefore, I can pick more than one at a time. So therefore, by window, I'm going to make a window. Believe it or not, I just picked all the top nodes. I don't know if you guys can see it, but it's yellow. Okay. And now because I picked more than one, I'm going to right click on the screen, go to properties. And of course, this is the Y direction and it's downward. So therefore, this should be minus 20. Okay. And of course, make that normal. So if I zoom in, okay, there's a minus 20, minus 20, minus 20. So each one of these have been assigned a load right at the panel point, or I should say at the node. Yes.
I don't get the same dialog box than you.
Okay.
Doesn't let me enter.
Did you pick nodes? First of all, here, are you here?
Yeah, I'm at nodes.
And you activate the node here, right?
Yeah, activate nodes, and then
okay,
I selected all the top ones.
Okay, click. Now I'm going to do it again for the bottom ones. Okay, so here I'm at activate nodes. I'm going to pick all the bottom ones here. Fair enough. Now see, they're all purple. They've all been picked. I right click.
Yeah.
I go to properties. And this is
that's the dialog box that I'm not getting.
What are you getting as a dialog box?
I'm getting a spreadsheet, and I can't enter any data. Like I've got load case, node number, FX, FY, FZ, MX, MY, MZ.
See where it says FY? That's where you have to put in the value. I don't know why you're not getting this dialog box. You're doing something. You're doing something to the program responding to what you did. So it'd be hard for me to know without going into your file. You understand?
Okay.
So what you're going to have to do is you have to, on your spreadsheet, you're going to have to go and apply in the FY, like in my case here, I'm going to be applying minus 250, okay? And there you go. And so there's my values there, you see?
Yeah.
Okay. Now, if you're not getting that, I don't know what you did. You could have toggled something on. You understand? Like it's hard. I have to go into your file to be able to see why you're not getting the same. Is anybody else not getting the same dialog box? Can you give me a heads up, please? Are you guys getting the same dialog box that I'm getting or not? Or is
Yeah,
everybody? You are,
Yeah,
Emmanuel?
yeah.
You're all getting the same one as I'm getting, and so like I said, be very careful when you're doing programs because a program is going to be very sensitive to what you toggle on, toggle off, switch on, switch off. So I don't know why you're not getting the same dialog box. What we can do, like once we finish the this example, or once we finish the lecture, if you stay on, we can open up your file and we're going to share your screen and we'll be able to see what you might have done differently. Understand? But it's very hard for me. It's very hard for me to guess what you might have like switched on and was switched off. I have no idea. Okay.
Yeah. Okay.
So I apologize for that. Like I can't understand. But you can still put in your values. If you're getting a spreadsheet, that means you have to put in the value of minus. Did you do it for? Are you at the top nodes or the bottom nodes?
Well, it doesn't matter. I tried, and no matter which node I click I click on properties, I can't even like edit the spreadsheet. Normally I can, but now I can't.
Okay.
I don't know why.
Can you do something for me? Right now, are you here? Are you activated a load case?
Yep.
You're there. You activate a load case, right? And here on the vertical, you're at activate node, right?
Yep.
Okay. Can you double click on one node?
Yes.
And what do you get as a dialog box for one node?
I only get spreadsheet and I can't write on it. It's
You
locked.
get, you get,
I don't
in
know.
other words, if I do this, this is what you get.
Yeah, but I can't write anything.
Well, first of all, did you put a plus sign here? Is it
There's not even a plus sign.
There's nothing in your spreadsheet.
No, and it's not even the same. Like your first column is node number, mine is load case, then node number. Is it because I didn't choose the right case?
Well, first of all, did you activate did you activate live here? What did you call your case?
I called it live.
You called it live. In other words, when you went back to your load cases definition, you called it live here. That's it.
Okay, yeah. Now I got the same dialog box.
Okay, you see. So
I activated the
wrong
I
one.
activated a load combination.
Exactly. You don't even have a load combination yet. You understand?
Well, I created it, so.
But you shouldn't. You should like work in the right steps. Because it's useless for you to do your load combinations without doing your load cases. It's useless for you to do your loads without doing your model. You understand? So everything follows in a sequence that guys, I used to have a program. I bought this back in 1987. Okay. And I thought that the guys that developed the program, this was back in 1987, the guys were really smart, okay? What they did is they put the menus, they put them in sequential order as you would need to be able to create and add the information in order to do your analysis. And I thought that the guys did a really smart job because they started with the section properties that you had to put in manually yourself, and then you had to put in your geometry, and then you had to put in your load cases, and then you had to put in your load combinations, and then you run your analysis. Okay, and believe it or not, in that program, 1987, graphically, when I used to put the support as the pin, graphically it showed me this little thing here, okay, on my screen. That's how nice the graphics were. And this was a 1987 program, okay? And I don't understand why ADA can't do the same thing. Anyways, I apologize for that. So now, so if you're able to do it now, like now you know what the problem is, okay? So now, so far we've applied our loads, right? We've applied our load, so we have no other loads to apply. I hope you all did this. And then, of course, we're ready to run some analysis. So therefore, before running some analysis, we've got to go to load. We've got to go to load combination, definition. Now, here, I'm only going to have one. Okay, I'm going to have live. I'm going to only look at my live loads for now. Okay. And like I said, I always like to run one. And then here, I'm going to call it live. I'm not going to put my dead load. I'm just going to put my live load. I'm not going to worry about this. I like to run live. So this way I can see if ADA is doing a good job, because it's easier for me to do some kind of verifications just with the live loads without worrying about the self-weight. And then if I need to add the self-weight, I'll come back and I'll do another one with live and dead. I'll just call it live for now. Fair enough. So now I've done my model. I've done my load cases. I told ADA how you want to combine those loads. I just want my live load ADA, and therefore I'm ready to do FX, static analysis. Save the project, analyze, and bang. Calculations complete, you may consult your results. That's super fast, okay? Now, like I said, whenever I'm doing any analysis, when I want to view my results, okay, first of all, I'm going to activate my live here. That's the only one I've, actually have. Activate my live. And this is the results. And here, I always like to see the reactions. I always like to see the reactions to see if it makes sense. Apply. And okay. And of course, bring them back to a normal height. Now, I can't see the values here, but if I want to double click on this, okay, sorry, close. Of course, I have to activate supports, and I double click on this. So here I can see the value, 675, okay. Look on this side, 675, okay. Now, if I do the sum of f of y's, it kind of makes sense that it should be symmetric. So in other words, equal 1, 2, 3, 4, 5, that's 1,000. 1, 2, 3, 4, 5, that's 1,200, and then 1,300 divided by 2, it makes sense. So the reactions make sense, so therefore, at least we're on the right track. Once I see my reactions, now, what you have to remember is that when everything is pinned in a truss, and I want you to understand this, when everything is pinned, the only forces you have are axial forces, forces running this way in the member, this way in the member. So you don't have any shear, you don't have any moments, okay? So you have forces, so therefore the only force you're gonna be able to see in ADA are the axial forces, okay? So, so that means that an axial force, if the member is running this way, okay, the axial force is either like this, okay, and that means that it's pulling the thing away, this is tension, or the axial force is like this, pushing the member together, and therefore that's compression. Now, how does ADA tell you which ones are in tension, which ones are compression? All the negative values are compression. All the positive values are in tension. And of course, it's very important that you know what members are in tension in steel and what members are in compression, because compression members and tension members don't have the same resistance. I don't know if you guys remember the first bridge that they built in Quebec City in 1906, okay? When they were building that bridge, the engineers didn't know anything. They didn't realize that the compression members didn't have the same resistance as the tension members. And as they were building the bridge, they were assuming that the members were in tension. And then as they built the bridge, the build collapsed and it killed about 86 people or 82 people. And it was really sad. And believe it or not, the engineer that designed the bridge, his name was Cooper. When that happened, he went into seclusion. He never built another bridge in his life. As a matter of fact, he sent a telegram telling everybody to get off the bridge when he found out the amount of deflection that the bridge was experiencing. And by the time the telegram there, it had already collapsed and it killed 82 people. So it's very important to know that. So normally, if the bridge, if this is how the bridge support, all these members on the top are in compression, these are in tension, and depending on the direction of the diagonals, these can be either tension or compression. So keep that in mind. As a matter of fact, I'm going to show you, okay? I'm going to show you, for example, if I show you, people say, well, I'm going to do MX, okay? You're going to see 0. Apply, you won't see no results. And that makes sense. You're not supposed to see any moments. If you see moments, that means you haven't modeled it properly because it's not a pin structure. Okay, they haven't been pinned. So therefore, now the only axial force you see, okay, the way MX, and now I'm going to do this here so that you guys, okay, this is the axial force for, okay, NZ. Okay, so you got to make sure that that's clicked on, and of course you want to see the values. Now, so if you want to, that's where it is. Okay, those are the axial forces. There's no shear force, there's no bending moment, it's only axial forces that you have. Therefore, if I click there, and I click there, and of course I don't want to see the supports anymore, I press OK, and this is what I see. Okay, now it's kind of hard for you to see, okay, up close, but if I zoom in, okay, so you see here, okay, so you see here you have, okay, you have minus 1,218.87 negative. That means that this member is a compression, and that axial force there in kilonewtons for that member there. This one here is minus 1,620, and therefore that's the axial force that you'd have to design that member for. It would be like a column that's subjected to 1,620 kilonewtons of force. Down here, this is positive, that means this is tension. Here, this is positive, that means this is tension. Here, this is positive, that means this is tension. Oh, here it's negative, that means this is in compression. You see, so that's where you see them. Now, what I'd like you to do for your assignment is that you draw the truss freehand like this, you understand? You draw the truss freehand, okay? And then I just want you to put the values for each member that you find in your analysis, okay? And I want you to do the same thing on the test. So you might as well learn, like, so just draw a freehand sketch, you know? I'm not asking you to be an artist or to draw it to scale, just draw a freehand. And then if you're not sure of how to read this, well, what you can do, okay, what you can do, for example, once you draw your truss and you want to know, for example, what's the value here? Well, I double click on this, okay, and it tells me, I'm sorry, first of all, I have to activate the member, I apologize. Okay, and it tells me what the axial force is right here. It's all negative. Remember, we asked for 10 segments, so it's giving me the value all along the 10 segments. But this is the force, the axial force in that member. So here, I would write on my sketch, I would write minus 1,216.87 if you really want to get fancy, or you can put it to 1,217. That would be accurate enough. And of course, okay, so if that's how you get, and if you notice here, there is no bending moment, there is no shear. There's only an axial force. Of course, you have displacements. Okay, close. And of course, if I want to see this member here, I double click on this and it tells me whether it's positive or negative. Therefore, I would put plus 250 for that member there, and so on and so on. So if you're having trouble reading it on the graph, which I don't like reading on the graph, number one, because it's hard to say which one applies to what. So if I want to make double sure, I simply double click on the member and it gives me all the information for that one member. Okay, it tells you the shape, this and that, and this, and of course, the right analysis, this should be all zeros, and you should only have axial NZ values, okay? And that tells you the NZ value. And that's, so there it is. That's the, you know, that's the, you know, that shows it to you graphically. I'm kind of used to this, but for example, if this here, okay, oh, it's positive. So that means that member is in tension. Oops, it's negative. That means that member is in compression. So I'd have to design this as a column, and I have to design that as a tension member. And what about this one here? Well, look at this one. 0, 0, 0, no, minus 20. So therefore it's in compression. Okay, so therefore it's got minus 20. It's kind of hard to see that, and you have to really zoom in, and therefore that would be minus 20 right there. So this member is in compression. Okay, and like I said, if you take the same truss and you turn it around, and you like, in other words, you take the other truss, like for example, if you take this around, you'll see that most probably if you take the same information, everything else, the only thing that's going to change is the compression and the tension for these web members. And now, last but not least, what I'm really interested in, okay, this is what I like about it, okay. if I want to see the joint displacement, okay, and this is what's nice about it, okay. And for example, remember this was pinned and that was fixed. So if I want to see the, for example, how this thing would deflect, under those loads, see, okay, so apply, okay, that's pretty good, okay. And if I go to nodes here, okay, okay, that gives me the, in other words, this thing only displaces 90 millimeters in a span of 54 meters. That's pretty good, guys. You see? And what I like about it also, okay, if I go to support here, okay, look at this. Okay, displacements. Well, believe it or not, just under the load, the joint would have to accommodate at least 31 millimeters of displacement. The joint, let alone the temperature and all that, just for the loads, it would have to accommodate 31 millimeters of displacement. And of course, if you would ADA, you can do a temperature also analysis and it would tell you what it would be like under, okay? So therefore, that gives you an idea, like right now, the expansion joint would have to at least accommodate at least 32 millimeters just for the loads deflecting under those live loads, okay? And that's what's nice about ADA. You can get all kinds of information to help you decide what size of expansion joint do I need here, and what, is this thing going to be sagging excessively under my loads? Do I need to make the member stiffer, and so on and so on? It's a great tool, guys, to tweak and optimize your design. So I hope you all got that, because now we're going to move on to another example. Okay. We're going to move on to another example. So I'm going to now we're going to model this one here. Okay, so we're going to start a new file. Okay, and again, we're going to go to, I hope we all start a new file, and we're going to be modeling this one here. So here I'm going to go just a touch faster. I'm not going to, hopefully you guys are starting to get the hang of it. And of course, the same thing. I go to File, Project Configuration, and Preferences, Metric. So I leave that in metric, not a problem. And like I said, remove these dialog boxes that are going to snap up in your face as you're working on it. Okay. And like I said, before I do anything, I like to always know my lengths, and I like to know my shapes, the materials. And at the same time, I like to get rid of that global axes. Now, here we're going to do the same thing. We're going to go to trusses, but this is a roof truss, and we're going to look, is this good for our, no good. Is this one good for, maybe, okay. Is this one good? No, it's rectangular, no good. Well, this looks pretty good, okay? In other words, I happen to have this member in the right direction. I know it's going to add another one here, it doesn't matter, but at least I'll be able to create that panel point, that panel point, that panel point, that panel point, that panel point. So I'm going to start with this, and then I'm going to modify it to my particular geometry here. So I'm going to start with a triangular Pratt on this one. And now, once I've done that, I come and put the span here of 24 meters. And I put the height here of 6 meters. And of course, I have 1, 2, 3, 4, 5, 6 panel points. So I'm going to put here 6. And I press OK. And this is what happens. Beautiful. Okay, so there you go. Now, I know it's not exactly the way I want it, but at least I have most of it the way I want it. I have the right height. I have at least 3 equal members here, 3 equal members there, and so on and so on. Now, first thing I'm going to do is, again, I'm going to start and make sure that I've modeled my supports, because this is something that's always overlooked. Okay, so I'm going to, now that I've got my basic geometry there, I'm going to make sure I'm on activate node. It should be there by default. I'm going to pick the one on the far left and hit the one on the far right. Go to properties, right click. And of course, I'm going to change this to a support. Okay, so now I just changed those to support, but now I got to model them correctly. So I'm going to activate support, and I'm going to double click on this one, Now it's a pin there, and of course a pin means that I fix X, fix Y, but I free MZ. That's a pin. Okay, and then I'm going to double click on this one. Sorry, all of a sudden I get the participants. I'm going to double click on that one, supports. X is free. In other words, I want it to be free to move along the X axis. I don't want it to move up and down along the Y axis, but I want it to rotate about that point. So I'm going to have free. Okay, so now I've done my supports. Great, because this way, this is something that always gets overlooked or doesn't get modeled properly, and you're always going to get a different result. Now, you notice that now, once I finish my support, now I'm going to start working on members. So I'm going to activate the members on the vertical column. Make sure you're on members here. And like I said, this one here, well, I don't really need it. So I hit the delete button and it's gone. Okay, that's number one. Now, does everybody got that? You pick the member. I'm going to undo what I just did. Okay, pick the member. Okay, you can either right click and you can delete, or you can hit the delete button as you wish. Okay, now you notice that these two members, okay, I don't like to leave them as two members. I like to leave them as one member. So I'm going to pick one, hold the control button, pick the other, or if you want, just draw a window around both of them. Either way. Okay, and if you come up here where it says join, I want everybody to find the join on the bottom row of the ribbon. Here you have join. Click that, and it says yes. Okay, okay. And now all of a sudden the program took that member and made it into one. And that's a nice little feature about the program, okay? So now I've got one member there and it's 8 meters. So far, so good. Now, you'll notice that here, I don't have this member. I don't have that member, okay? I do have this one. This is good. I have that one. I have that one. I have that one. I don't have this one, and I don't have that one. Okay, so I can get rid of them. So what I'm going to do is, of course, so again, I'm going to pick that one, hold the control button, pick that one. I'm going to keep that one, keep that one, keep that one, pick that one, and pick that one. And of course, hit the delete button, and now they're gone. Right? Now, before I forget, now that I'm going to take this member here and this member here, just like I did the one in the middle, I'm going to join them. I'm going to pick this member here and pick this member here, and I'm going to join them. So far I got my 8 meter member there, 8 meter member there, 8 meter, but I'm missing members here. So just like I would add, members between new nodes, I would hit the plus sign, okay? Add a member from there to there, and then add a member from there to there. Now, doesn't that look like my geometry? So guys, with ADA, you can start with a general geometry that's very close. I could have picked anything and it would have just required more editing or more modifying. So I picked something that is as close as possible to what I needed. What I needed here was at least three panel points on this side, 3 panel points on that side, equally spaced. That's what I needed. I needed these members to be in this direction. But most important for me was where the positions of the panel points were going to be created by ADA. So therefore, the nodes will be at the right location. Okay, so that's what was important for me, and that's why I picked that one. And of course, that was a triangular Pratt. Okay, truss. So now that I've got my geometry all worked out, in other words, I've got the right member lengths, I got the right number of members, and so on and so on. Of course, now I'm going to go and assign, hit escape out of the, okay. So now I'm going to go assign the members for the top chord, pick one, hold the control button, pick the other one, 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 right click, go to properties. And of course, this happens to be a WT. A WT is a Y flange that was cut in half that looks like a T. So therefore, I'm going to go to steel. I'm going to look for, here's my WTs. And of course, here are my WTs. And this one happens to be a 100. So in other words, it was cut from a W200. That's why it's a W100. And of course, this one weighs 13.5. And there we go. Press OK. Now, I'll assign the material all at the end. Okay, so I press OK. Now I'm going to pick this one, and this one. Right click, go to properties. And again, steel. This is also a WT, but it's a little bit smaller. It's a WT by 75. So I go to WTs here, WT here, W3 by 75. In other words, this was cut from a W1 150 and 75 by 9, and it's right there. So that's the one. Okay. Okay. And then last but not least, all the chord members are the same, so I can pick them all at the same time. Right click, properties. Now this happens to be two angles back to back. Okay, so these are two angles back to back. So I'm going to go to steel. These are two angles back to back. So this is where I have my 2LL here, my two angles back to back. So I have my 2LLs back to back, and they're 51 by 38. So I go to 51 here. So in other words, the long leg measures 51 millimeters by 38. Okay, 51 by 38. And of course, I want to go get the thickness of the leg, which has a thickness of 4.8 millimeters. And there's the, okay, so that's where I find it. Two L's back to back. So what this means is that these angles measure 2 inches by 1.5 inches, and the thickness of the legs are 5/16 of an inch, or 0.48. Yeah, sorry, 3/16 of an inch. In other words, these are actually in imperial size that have been converted to metric. So that's okay. That's where I get my, okay. Now I press OK. Now remember, the only thing I haven't done yet, I haven't assigned the material and I haven't pinned everything yet. So what I'm going to do is pick all the members at the same time. Okay, right click, properties, and I'm going to go to material. Make sure I assign the material. So therefore this is G350W. So I'm going to go to steel, G350 40.1 350W. So this is the steel that I'm using. Like I said, if I eventually want to include the self-weight, I'll make sure I activate it here. And last but not least, make sure everything is pinned, because a truss has to be analyzed as if all the members are pinned. So you free both ends. Make sure there's a 0 there and a 0 there. Okay. And like I said, I don't see the end condition here, but if I want to make sure I'm on the right side, I'm going to go to attributes, end conditions, apply, and there you go. You see? So this is perfect. So I've got all the right end conditions. I've got all the right member sizes. And then of course, I want to make sure I assign the right material. Go back to elements, go to materials, apply. It gives me the material, the material, the length and all that. So everything looks good. I'm quite happy. My supports have been modeled properly. Well, I'm ready to do my load cases. So I'm going to now, excuse me, I'm going to remove all of this so that I don't have it when I'm looking at my results. Remove all of this right now. Apply. Okay. Now I'm going to go to load cases. I'm going to define my load case, and now this one I'm going to call a snow load, because most likely it's a snow load that I'm being applied to a roof truss. And I'm just going to call it snow. Like I said, if you want, you don't have to, but if you want, you can define it for the program. That's how you define it. Okay. Now you're ready to apply loads. So you have to first activate the load case. And of course, I'm going to be applying snow loads. Save projects. Okay. And let's go back here. Okay, so here we go. So now, like we did before, now these are applied at the nodes. So therefore, I'm going to activate nodes, number one. So when I go pick on the screen, the program is going to pick what the element that I wanted to pick. That's number one. They all have the same values here. So therefore, I can pick them all at the same time. So I'm going to pick all of these at the same time. And you'll notice that they turn purple, 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 perfect. Okay. Right click, properties, and that's going to bring up the dialog box. And of course, this is negative. It's going downwards, so minus 2.5. Okay. And there you go. Now, if you want to see them a little bit bigger, you know, you can always do this. You can click on this until, and if you want to see the writing a little bit bigger, okay. And that looks pretty good. So I've got my loads in, nothing else to be done. My load cases have been completed. I've applied them to my model. Now I go back to load. I do my load combination, definition. I'm going to add one. I'm going to call it snow. Okay, and then of course here is where I define, okay, snow. And of course, the only thing I want to do is apply the snow load, not the dead load yet. And by doing this, you can actually see the deflection of this truss that it would go under this particular load. I've done my model, done my load cases, told the program how to combine my load cases. Now I'm ready to do the FX. Yes. Analyze. And it's already done. So close, and just like before, like I said, what I want to see is, you know, I want to see my axial load. So therefore, I'm going to do this. I'm going to go look, like I said, I like to look at my reactions. Okay, apply. And this makes sense. Okay, so 1, 2, 3, 4, 5. So in other words, that would be 15, and that makes sense. So that makes a lot of sense. And once I looked at my reactions, I'm happy with my reactions. Then, like I said, the only thing I should have is the NZ values. Okay, apply, and of course they look very small. If I want to make them bigger, I simply click on this until, you know. So what I don't like is that it gets really messy in here and it's hard to see. Okay, so like I said, if ever you want to know like what this member is here, you just double click on it. Oh, negative value, compression 2.5. Okay, and therefore if you're having trouble seeing and you're not sure what you're looking at on the, so in other words, these are all in compression, so they draw below. These are all in tension, they draw them above. That's what ADA is doing. This is below because it's in compression. This is above because it's in tension. Okay, and so on and so on. But if you're not sure, just double click on the member, and this is where it'll tell you whether it's tension or compression. Okay, and of course, last but not least, if you want to see the deflection of this truss under this loads, okay, or the displacements, then you take this off. The deflection about the strong axis, apply. And that tells you that this truss would deflect 2.77 millimeters over a span of 24. That is very stiff truss, trust me. And there you go. So that's the nice thing about ADA. It does all the analysis, it gives you all the force, and then of course you'd have to design the forces. You have to design the members to be able to resist those forces. And then next year, you should be able to do that in your wood project when you're doing the truss analysis and the design of the wood truss, okay? So now I got one more example to show you, and this one is more for your general information. I want to show you the difference between when you have members that are continuous in the truss and some members that are pinned, okay? That's what I'm going to be doing another one. So this one here, okay? So here what's happened is that I'm going to show you, for example, this is a real wooden truss. In the wooden truss, this member here is continuous. This member here is continuous. This member here is continuous from here to here, but it's pinned there, continuous there, pinned there, and all the wood members are pinned. So this is really a real wooden truss, how you would have to model it. And of course here, okay, it's got a span of 25 feet. It's got an overhang of 1.2 feet and so on and so on. So I just want to show you how you would handle this with ADA, so that you'll realize that you can leave certain members continuous as AD does by default, and which ones you would have to release, okay? So let's go on and start a new model, okay? Let's start a new file. Now, of course, here I'm gonna have to go to File, Configuration. Now here, everything's in Imperial. So first of all, I'm gonna make sure I'm in Imperial as far as and even my members are Imperial. 2x6s, that's all Imperial, okay? So both my sections are in Imperial and my geometry is Imperial. And then of course, remove these dialog boxes. Apply. Okay. Now, like I said, I always like to see my member lengths and the shapes. And of course, I like to see the end conditions when I'm going to be pinning, and I like to get rid of that graph. Apply. Okay, so here we are. We know we're at a roof truss. So therefore, what we're going to do is going to go to trusses. And now, this looked pretty good before, but I want to see if there's something that's a little bit closer to what I need to model. And therefore, I'm going to go here. That's definitely not. And then this looks pretty much, believe it or not, this looks pretty much what I want to model. In other words, I want to model here these two members here with three, you understand, three equal members for the bottom chord, and having here only, you understand, depending on how many I would put in, I would end up to. So I'm going to start with a Fink truss. Okay, I'm going to start with this, and here the span is 25 feet. And of course the height, I should have given you the height, but I'm gonna have to calculate the height. I should have put the height in. So 25 divided by 2 equals 12.5 times 4 divided by 12 equals. So the height is, I'm sorry, I should have put the height on the diagram, but the height, you can calculate with the slope. You're gonna be putting 4.17 feet for the height. I apologize. And of course I have 1, 2, 3, 4 panels. I need 4 panels. And I'm going to press OK. And there you go. So here is the, okay. So now this is what I get. In other words, I get pretty much, okay, I get pretty much what I want. I'm going to make these a little bit smaller, okay. I get pretty much what I want. In other words, this here is okay. This here is okay. The only problem is that this here, they should be at 8 feet 4 inches, okay? And then this should be at 8 feet 4 inches. So what I'm going to do is very simple, okay? I'm going to go to my structures. I'm going to go to my nodes. Okay, first of all, I should explain something to you, okay? Like if I double click on this node, okay, this should be at 8.33 feet. So I can change the X coordinate right away. And now I put it there. Now, 8.33, 8.33. And then this one here should be at 16.67. So in other words, this node here should be at 16.67. So I double click on it. So this should be at 16.67. Okay. And there, and now I've got basically, don't worry about, I know this is supposed to be 8.3, they are all the same length, and that's how I'm able to adjust the geometry simply by changing the coordinates of the nodes, okay? So that's number one. And then after that, I basically, if I want to create, okay, now after that, if I want to create, for example, this overhang here, I'm going to create this overhang here. All I got to do is add a node there, and I just need to know the coordinates of those nodes. Well, here it's definitely, it's minus 1.6 feet, and it drops down by 6 and 12. So in other words, this drops down by 0.5 feet there, and that's going to give me the, and if I know the coordinates here, so I can create those two nodes. And then of course, here's the same thing. I got to go and put a node here. So this is 25 feet. So in other words, that would be 26.5. Sorry, 26.5 feet. And then of course it drops down by half a foot, 4 and 12. So what I need to do is, of course, go to my structures, go to my nodes. I'm going to add 2 more nodes, 1 and 2. Okay, and these are going to be normal. Okay, and therefore the first one I'm going to be putting at minus 1.5 and minus 0.5. Oops, sorry, minus 0.5 there, minus 0.5 there, minus 0.5. And the other one will be at 26.5 and minus 0.5. Okay, so now I've cleared all my drawing. Okay, so now I've created the 2 nodes that I can, and then of course I can add my add my members. Cancel. So now I can add members. So therefore I can add members from there to there. And I can add a member from there to there. Okay. Now, of course, what I need to do now is this member here is separated. So I click on that member. Okay. And I say split the member. Now, if you're not sure, you just put it there, and then you want this to be at 12.5 feet. Okay. 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 Oh, I made a mistake here. Sorry. Okay. It's because I wasn't, hold on a second. Delete. Oh, undo. Undo, 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 undo. Okay. What is this doing here? Anyway, I better undo. I don't know why I have a node here. I have to go check my structure. Nodes. Oh, here we go. That's what's wrong. Delete. Okay, so that was wrong. So I'm sorry about that. I accidentally, okay, I'm going to go back to add my member. Add my member, escape. Okay, like I said, now I'm going to be on member here. So I pick this member and I tell the program to split the member. And I don't worry where I split it because I can go back and change the coordinates. Okay. I'm getting some kind of error message here. Okay, I got a problem. And this is the typical thing about members. Delete. Okay. I'm sorry. I'm going to have to do the long way. And I apologize for that. For some reason, I went a little too fast because I don't want to take up all your time. But right now, what I'm going to do is I'm going to add a member. I'm going to add a joint. So I'm going to go to structures. I could have just split them. I'm going to add another node. It's going to be at 12.5 and 0. Okay. And there it is. Now I'm going to just simply add the member. So that, like, I don't fuss with the program. There we go. Okay. So now I've got my geometry, like I said, and I apologize for the thing. I'm not going to like, so there is the geometry. Like I said, with ADA, I can go to the spreadsheets. I can fix anything up. Now, I just have to remember that with ADA, all these members are pinned. So I pick these members here. Okay. I right click and I go to properties, and therefore I'm going to pin them all. They're all pinned. Now, this member here happens to be pinned here and continuous there. So I'm going to go to properties and there you go. And of course, this member is pinned to this member here. So I'm going to go to properties. Oh, wrong side. So I just go back, properties, and just change it. Okay. And of course, this member is pinned to the top chord, properties. There you go. So there you go. So now I've pinned all the members that were supposed to be pinned. In other words, this would be a 2x4 that would be continuous across that panel point. Therefore, it should be continuous. This is a 2x, and these two are joined together at like this. And this is a continuous member. And this member should be pinned to the other members here. So I'm going to go to properties. And I'm going to do the same thing. And of course I did it on the wrong side, so I don't care. Just go back. So guys, like that's why I like to see it graphically. So there, now my model is pretty well complete. Okay, and now of course I would go and assign the members. So in other words, just like we did before, like I said, this is just for your general information that you can have continuous members and members that are only pinned, like the web members are always pinned. You can have continuous members, and you right click, go to properties, and here of course you're dealing in timber. You're dealing in rectangular timber. And here you go. And we said that this was a 2x6, so therefore you go into sixes and, oh, sorry, I'm in the wrong, I should be in the twos here, not the sixes. So you're in a 2x6, and therefore that's where you find a 2x6, okay. And of course, we'll assign the material, it's all the same material. And then of course, these are all the same, so therefore I'm gonna pick them all at the same time. Right click, properties, go back to timber again, and go the same thing, rectangular. So what I like about ADA, it has quite a bit of information in the database, okay? This is a 2x4, okay. Oops, okay, and now of course I'll pick them all at the same time so that I can assign all the materials at the same time. Properties, and if the material is this way, I can go to timber. This is a visual grade. This is an SPF, number 1, number 2, visual grade, and therefore, and of course, if I want to include the dead load of the truss, I put the dead load. Okay. So now I've assigned my members, right? And now I'm ready to do my load, okay? And the dead load on the top chord and the bottom chord and so on. And I would just keep on assigning my loads, and I can, okay, so in this case here, I would definitely get rid of all the information. I've done everything I needed to do, so I'm going to remove that, remove the end conditions, apply, okay. So now here, of course, I would have dead loads and live loads, so therefore I would go to load cases, definition. So therefore, and in this case, I like to call this SID. That's a superimposed dead load over and above the dead load of the structure. That's what I like to call it. And then here I would have, of course, my snow load. And I would have my snow load, of course. Now here, this is where you have different load cases. So for example, here I say that the dead load of the top chord is 2.5 kPa, okay? And the truss are spaced at 0.61. So what you have to do is you have to multiply that 0.25 times 0.61. That would be 0.153 kilonewtons per meter, because you have to apply a uniform. So therefore, I would activate this, my superimposed dead load, save project, yes. Why doesn't it go to where it's supposed to go? So now I got my superimposed dead load. This is applied to the top chord, so I would pick all my top chords here. This is you'll see, guys, this is a little, you know, and this is just for your general information. I'm doing this. You're not going to be tested on this one. You're only going to be tested on one of the first two that I gave you. So superimposed dead load, right? Right click, properties. It's a distributed load. And of course, it's, now this is in kPa. So I'm going to change my units. Change units. And of course, I'm going to change it to kilonewtons per meter. So I don't have to, 2 decimal places, okay. So I have minus, so I have minus 0.153, minus 0.153. Now, the nice thing about KPA about the program is that when you're applying the top chord, because it's at an angle here, it has to be applied perpendicular to the angle. So therefore, you'd have to change the angle rotation, okay? And you apply it to the strong axis. And if you do that, of course, bring it back to something normal. And that's how you tell ADA to apply it perpendicular to the member here, okay? And then for the bottom chord, you have 0.2 times 0.61. So the bottom chord would be a slightly lighter load. So I would do the same thing. I would pick that one, that one, that one, and that one. I forgot to release it here, so that would give me a wrong answer. My modeling is not totally correct. I forgot to, I don't remember if I released it there. So basically, do the same thing, right click, properties. So here I'm going to put minus 0.122. And that's now here because it's 90, I don't have to do it to the strong axis because it's going to be perpendicular to the member because the member is horizontal. Now the last one is a snow load. So I would change the load case, go to snow load. And then here, the snow load is 2.4 kPa times 0.61. And that comes out to be minus 1.464 kilonewtons per meter. And therefore, I would say, I would pick this member here, the top chord, the top chord, the top chord, the top chord, the top chord. And of course, I would properties, and I would put minus 1.464. Okay. Now, this is what's nice about ADA. It allows you to put the, okay, horizontal global. And that's how the National Building Code wants you to apply the load. And that's what it would look like. And that's horizontal global. So the ADA applies a load according to the way the code, in other words, it has to be totally horizontal across, even though the angle of the member, and ADA will analyze it correctly. And of course, now that you've done your load cases, then you would go to your load combinations. Okay, so here, for example, if I was doing this, okay, if I was doing this for the to analyze my truss, and I was doing using a design method, I would call it limit states, ultimate limit states. Okay, and in this case here, I would add the 3 loads to get my strength analysis, and therefore the first one would be the dead load, the second one would be the superimposed dead load, and the third one would be the snow load. And if I was doing this according to National Building Code, the load factor here would be 1.25. This is way above the scope of your head. Don't worry about this. It's just for information. This is 1.25. And for the snow load, you'd have to multiply it by 1.5. And that's where you would actually be doing it. You press OK. And then once you've done everything, you're ready to run your analysis, save the project, analyze. The support node does not exist. Oh, I forgot to put my support node. See, I got an error message. So right away, I'm going to have to go back to my structures. I've already skipped a step. You see how easy it is to overlook the support? Go to nodes. So I have no supports. 1, 2. Okay. Right click properties and change this to support node. Okay. And then go here to supports. And this is the, okay, so I'm going to make that into fix free. Okay, and I'll go here, free, okay. And of course, now I'm ready to run the analysis. So you can see, guys, I overlooked the, because I don't want to keep you past 12 o'clock. So I'm trying to do this as quickly as possible. Analyze and member shapes not assigned. Okay, so there's something I have not assigned here. Probably, let me see if I go back. So this is, guys, I'm doing this not really on purpose, but to show you every time you get an error message, you got to go back and you got to try to find which one. Okay, so it says member shape not assigned. So shape, apply, and it says I haven't applied the shape, and therefore I haven't applied it to this one. Okay, so therefore I have to now, so ADA needs all the information in order to timber, rectangular, rectangular, okay, and now let's try again. So let's try running the analysis. So guys, every time you overlook something, analyze, wow. There you go. So now I see, so if you forget to assign a member, if you forget to assign a material, if you forget something, ADA will give you an error message. And then of course, here's my thing. And then let me go remove. I just want to check one thing to see if I did the right thing here. Yeah, I did. Okay, so I just wanted to make sure I did that properly. And I'm going to take off shapes, apply. Okay, oops. And of course, now I can go look at my results. And in this case here, believe it or not, we will have some bending moment. We will have some shear. We shall have some reaction. You know, I'm doing this just because we're almost at 12 o'clock. I don't want to go over 12 o'clock. And of course, here, make everything. So here are your bending moments. Here are your shears. But you should look at this individually. Here are your reactions. And this is what your truss would have to be analyzed for. So guys, on that note, I apologize. I rushed to the last example. I did it more for your general information than anything else, so that you can realize like how elaborate things can get, or like to what extent you can use ADA to do your analysis to properly reflect what your structure looks like. And that's it. So does anybody have any questions? No? Okay, so I'm gonna, hold on a second. I'm going to stop. Okay, so if we're all good, I'm going to be sending you, I mean, this, I don't know if I should send you the lecture. The lecture is just the example, but okay, now, just to recap, remember next week we're going to have our second test. Okay, it's only going to be, you're going to, like I said, 3 problems. The 4th problem is a beam problem with a pin. It's going to be done on ADA, so you can use ADA. And the first 3 problems are going to be calculate deflection by superposition, calculate the supports by superposition, and calculate the transformation of material of a section. And okay, so let me just, before we call it a day, does anybody have any questions? Hello, are you there?
Yeah, well,
Yeah.
Okay, thank you for answering, because I'm trying to minimize all this stuff, and all these menus are in the way. Stop sharing. Okay, so guys, I know I took up all the time today, but I really, so like I said, the 3rd problem was just, the 3rd example is just to show you like if you have continuous and non-continuous members and so on. So don't worry about that. That's not going to be part of this course. Just worry about how to do the first 2 examples properly. And if you guys have any questions between now and the test of course will be start at 10 o'clock. And I'm going to do the test myself to see how long it's going to take me to do it, you know, manually and with the ADA. And what I usually do with all my tests is I take the time it takes me to do the test and I multiply it by 2. And if I see you need to take the whole 2 hours, I'll give you the whole 2 hours. If I see it takes me 45 minutes, I'll be giving you an hour and a half. So be sure you know what you're doing, because the time's going to be, you're only going to have twice as much time as I would have to do the test. And okay, so I'm going to